With the third lecture, uh, and this is devoted to the fundamentals of species. Here we will talk about the definition of the surface active species, what problems species absorb at the interface. Mainly we will be talking about the surfactants and their interfacial properties. One need to understand the fundamentals of surface active species. As I mentioned last time, without the surface active molecules or the amphiphilic molecules, we cannot produce the stable colloidal suspension. I mean to say that when we have to produce a nanoparticle, and in the aqueous phase, if this is the nanoparticle, we need to create a bilayer around the nanoparticle, and this bilayer around the nanoparticle is created by the surface active molecules. So how the surface active molecules are going to compare, that adds the colloidal properties and hence produce the stable suspension is being used for different kinds of applications. What is the meaning of a surface? Suppose if somebody asks you in terminology this surface is interface between the solid substance and that of the gaseous environment. So exactly the same way, wherever there is interface, no the surface. So here, so we can say, but in fact, this is the interface between the immiscible phases. The molecules of the air, they do not want to mix with the molecules of water because of their entirely different properties. Molecules of water, they are polar, whereas molecules of air, they are non-polar. Hence, practically, there is negligible miscibility among the molecules. Surface active molecules, they have the ability to simultaneously interact with both phases, the polar phases as well as the non-polar phases. The polar phases, towards the polar phase, the surface active molecule includes its polar functional group, whereas in the non-polar phase, the non-polar functional groups are embedded in the non-polar phase. Therefore, a single molecule possesses dual ability to simultaneously interact with the two miscible phases. This is because that molecule is possessing polar functional group as well as non-polar functional group. How we can generate such kind of molecule? If you simply look at this molecule, and if you ignore it, there are three methyl groups. And if I replace this hydrocarbon chain with the methyl group, this is ammonium, alkyl ammonium substituted ammonium ion. If I am going to remove one alkyl group with the hydrocarbon chain, it means that the non-polarity that was incorporated by the methyl group has been enhanced by the number of methylene groups. So this functional group possesses predominantly non-polar character, whereas the head group possesses predominantly polar group. So therefore, overall the molecule, basically it is the ion. If you ignore the bromide, and this cation possesses two functional groups. The one is the polar functional group, the other one is the non-polar functional group. Such kind of molecules cannot entirely solubilize the aqueous phase. Either they can be solubilized in the non-polar phase because of the polarity they are possessing. So therefore, these molecules are forced to be accommodated only at the interface. So the part of the functional group that is polar in its properties, that is going to interact with the polar phase, the non-polar part, that is the non-polar functional group, that is going to interact with the non-polar region of the other phase. So these molecules, the non-polar part is known as hydrophobic. It has no ability to interact with water, but it has kind of a phobia of water. It runs away from the aqueous phase, whereas the hydrophilic group, it is polar and hence it has the ability to interact with the water molecules. This dual ability of a molecule possessing the non-polar and the polar functional group, or possessing the hydrophobic and as well as the hydrophilic functional group in the same molecule, they are known as amphipathic structures. Now, such molecules, they are required in order to create a stable colloidal suspension, because if we are going to arrange at the air-water interface, because that is much easier for us to understand, so they can also arrange themselves at the solid-liquid interface. So therefore, if the molecules are going to be arranged at this interface, suppose if you ask me how many interfaces you could see over here, the one is over here, that is between air and the fluid phase. Other one is over here, that is between solid and the fluid phase. Another one is over here, solid and the gaseous phase. So the molecules, because these molecules, they reside in the fluid phase, so therefore they occupy all the interfaces. It's not only the air-fluid interface, but they also occupy the solid fluid phase. That solid fluid phase here, our main objective is to understand that how the molecules, they are going to absorb at the nanoparticle interface, that the solid fluid interface. How we can synthesize them? The most prominent example for the synthesis of the amphiphilic molecule is the saponification. It's the soap making chemical reaction, and it's the esterification. You know that we can take the ethyl stearate over here and we treat with the sodium hydroxide, and this way we can create the soap. It's the salt here, the sodium stearate. We create the sodium stearate. Now, this soap, you know very well that it has the amphiphilic property, exactly the way we are showing over here. The only difference, it's the same kind of a molecule. So here we are dealing with the anion that has the amphiphilic properties, because here the cation is not a surface active ion, but the anion is the surface active ion. Here it is the cation and the surface active ion. Now this anion, which is the surface active ion, so it has the ability to interact or to absorb at all the interfaces. For the sake of clarity that how this anion acts as soap, we only show, suppose if we have the suspension of oil, that could be in the aqueous phase, or the oil could be on your any kind of clothes, and when you are going to immerse the clothes in the soap solution, what happens? You may see this oil may be on the surface of the clothes, or it is embedded in the aqueous solution. So as soon as you are going to add the soap, this oil is non-polar molecule of the non-polar phase. The non-polar functional group of the amphiphilic molecule, so that is going to be embedded in the non-polar oil, whereas the polar function groups, they will remain in the aqueous phase. Now you could see that by inserting the tails into the oil, it increases the solubility of the oil in the amphiphilic molecules aggregated state. So these molecules, they aggregate or arrange at the interface, that is oil aqueous interface, and hence they pull the molecule from the solid surface and they dissolve them into their aggregate. So this is the aggregate of the amphiphilic molecule, and the solubilization of the oil is only happening, or it is only driven by the hydrocarbon tails of the hydrocarbon chains of the amphiphilic molecule, and this way the oil particles which are sticking to the surface of the clothes, so they are being picked up by the soap solution. So this mechanism is always working during the washing process of the dirty clothes in in the presence of soap. Now, the most important thing over here, you have seen the aggregation of the molecules in the form of a spherical shape. What forms the aggregation of molecule in the spherical shape? Or in other words, if somebody asks you, I can understand that the stability of the colloid is important because you need the bilayer in order to stabilize it so that this particle should not interact with another particle like this, and the particles remain suspended in the aqueous solution to make a colloidal suspension that has a stable colloidal phase. But the problem is, what concentration we should take? Is there any kind of judgment or the estimation that which concentration is required so that we can completely coat the particle? So now that is the most important aspect here. If you have the required amount of the concentration that is less than the ability to provide the bilayer, the colloidal particle is not going to be stabilized. So therefore, the concentration of the amphiphilic molecules must be much greater than the concentrations required of the particle. But how we can do that? We need to use for the layer around the nanoparticle, and that is related to the behavior of the amphiphilic molecules to aggregate in the kind of spherical. What are the different kinds of molecules? See, here so it means that the surface ion for a molecule could be predominantly negatively charged or positively charged, or it could be neutral as well, but it has the ability to interact with the phase or the aqueous phase. On the basis of that, the surface active molecules are divided in different categories. That is, here the head group is positively charged. You see the ammonium, phosphonium, again ammonium, right? So these are we have changed the length of the hydrocarbon. This is tetradecyl C14. This is also tetradecyl C14. This one is hexadecyl. It is C16. So C16 hydrocarbon chain length. I mean to say, somebody asked you that what is the meaning of that? The end of this line represents the methyl group CH3. Here it is CH2. So I can just let you know how to count the length of the amphiphilic molecules. So it is CH3, CH2, 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 CH2. How many? 1, 2, 3, 4, 5, 6. And if I keep on going, CH2, CH2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And so you need 3, 4, 5, 6, 7, 8, 9, 10, 11. And here you have the last one, CH2, and then that is connected to ammonium group. So it could be CH3, CH3, and CH3. So you can see 1, 2, 3, the one starts from this side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it is C12 hydrocarbon chain. So C12 is dodecyl. So dodecyl hydrocarbon chain, and in this way you could have dodecyl, and likewise you have tetradecyl and hexadecyl. So the meaning for tetra is, so there are C14 and C16 methylene groups, so those are present in the hydrocarbon chain. Right. On the basis of that, it is the nomenclature we use for the surface active molecules. The rest nomenclature, where we have to talk about that what kind of ion or cation is, that is related to the presence of particular element, which is having the quaternary structure. Here you see the nitrogen, ammonium, and here it is the chromium. And then you see the phenyl group, and here they are the methyl group. So these terminal groups could be anything. So most of the time they are identical, or they could be non-identical or different function groups as well. So you see now, if I'm going to increase the chain, by increasing the chain, what I'm going to do, I'm increasing the known polarity. So known polarity increases as the length increases from C12, C14, C16 and so on. By increasing the known polarity, I am increasing the known polar, the ability of the functional group to interact with the known polar phase. So known polar, a known polar ability of the functional group that increases, or you can say the van-der-Waals interaction with the HEPO, which it can interact with the other known polar phases, so that increases. And here you could see different kinds of surface active molecule. This one is when you have to identify the surface active molecule, you must keep your attention on the charge of the head group. So this is known as a head group, right? So you can say that, I mean to say that you can depict the surface active molecule, the surfactant, in the form of a tail. If I'm showing the tail over here, and the polar part is the head. So this is the polar part, you see. So it is the tail and head. So tail is non-polar and the head is polar. So it is identical to the molecular structure of the molecule. So usually when the surface active molecule is depicted in this schematic form, so it is automatically demonstrating that the tail part belongs to the hydrocarbon chain length and the head group belongs to the polar part. So on the basis of the head group, you can divide the molecule into different categories. If the head group is positively charged, it's called cationic surfactant, negatively charged anionic surfactant. When the head group is possessing no net charge, but it has the ability to interact with atmospheres, we call it the non-ionic surfactant. And when the head group is possessing the dipole, means it has the positive net charge as well as the negative net charge, so then we call the Zwitterionic surfactant. So you can choose any one depending upon the fact, or most of the time for the colloidal stability of the gold nanoparticle or the transition metal nanoparticle, that could be the gold, silver or platinum. So it is better to use the ionic surfactant. You may use the cationic or the anionic surfactant, and they provide much better colloidal stability because the adsorption, I think I showed you over here. Okay. So the adsorption on the surface, suppose if I say that this is the surface of the particle. This is the surface of the particle, nanoparticle. I am simply writing NP. Right. So then how the surfactant is going to adsorb? It is going to adsorb like this. Right. The head group is going to be adsorbed on the surface rather than the tail. Now, if somebody asks you that what prompts the head group to adsorb on the surface of the nanoparticle, you'll be saying the transition metal nanoparticle, like gold nanoparticle, they have the free electron cloud that is mobile, and hence the surface is charged. So therefore the charged surface is going to interact with the charged head group rather than the tails. So usually the tails are not going to adsorb on the surface of the molecule, it is the head group. And since the tail cannot stay in the aqueous phase, so therefore another layer of the molecule is going to be arranged in the inverted direction, so that the tails are going to interact with the tail and these head groups are going to interact with the water molecule. So therefore, now this is solid liquid interface. Solid liquid interface. Now the solid liquid interface, exactly the way the air-water interface is being occupied by the surfactant molecule. So here in the case of the nanoparticle, this is the solid liquid interface that is going to be possessed or occupied by the surface active molecules. If you need a stronger adsorption, much stronger adsorption, then you could see that this is the single tail, right? If I remove another methyl group, suppose if I am going to remove another methyl group over here, I can introduce another tail, another hydrocarbon chain, just like that of the previous one. So here I have another hydrocarbon chain. You see, one is over here. This is the first hydrocarbon chain, and this is the second hydrocarbon chain connected to the same head group, right? Or we can have the two head groups. Suppose if I say that there is, let me remove this, just a minute. If I alter this, so I have two ammonium groups, okay? So now I have two ammonium groups, CH3, right? And I have two ammonium groups, you see. So it means that you may say that it is the double head group. Yes, if the length of the spacer is long, so we can say it's double head groups, right? And the double head groups, one head group is connected to one tail, another head group is connected to another tail. Such kind of molecules are known as Gemini. Gemini molecules. You see over here the difference. The diagram, the sketch here, what I am showing, by replacing one methyl group with that the second hydrocarbon chain. And so by doing so, there is one possibility that I could keep just one ammonium functional group and two tails, or I can have two ammonium functional group. One is separately connected to one hydrocarbon, another one is connected to another hydrocarbon chain. So here is the comparison. When you have the one hydrocarbon chain, we call it monomeric. When you have the double hydrocarbon chain, we call them the dimeric. So see over here, this is one hydrocarbon chain. It is C12. You can have identical C12 here, C12 and C12. And you see there are two head groups. The one ammonium functional group, another one ammonium functional group, and they are separated from each other through a spacer. We call this a spacer. The spacer could have any length. It could be of just one methylene group, 2, 3, 4, 5, any spacer length you can introduce over here. You can increase the spacer length, right? But you have to keep in mind that you are putting more methylene groups in spacer. Obviously, you are reducing the polar ability, the polar ability of the polar functional group by placing the non-polar, because methylene groups are non-polar. CH2 over here. So by putting the non-polar functional group, in fact you are reducing the ability of the head group to interact other polar faces, because there is the non-polar functional group that is inserted in the head group region. So such kind of a molecule is known as Gemini, only as Gemini, because there are particle hence we call them a Gemini molecule. So dodecyl is the length, trimethyl ammonium bromide, and likewise hexadecyl trimethyl ammonium bromide. But here you might be remembering the nomenclature. So when we have the two identical functional groups, so we use bis. So dimethylene means it is the spacer, it is referring to the spacer. Di means there are two methylene functional groups connecting to bis. This means the two identical, you see the two identical dicyl dimethyl. Dicyl refers to C10. Dimethyl, so dimethyl are the methyl function group on the positively charged nitrogen. So dimethyl ammonium bromide. So it is bis. It means that there are two functional groups exactly of the same molecular structure. So that's why we are using bis. Likewise over here you can see again dimethylene. Again there are two methylene groups. Those are creating the spacer. And we have dodecyl bis, dodecyl dimethyl ammonium bromide. So in this way we have the nomenclature. We use the name IUPAC name for naming the acrylic molecules, surface active molecules. Now, how we can determine by simple experiments that they are really surface active? Obviously, if we need to understand they are surface active, the most important property is the interfacial tension. So, the surface tension of the water in the absence of the surface active molecules is close to 61 or 62 millinewton per meter. So, and when we start adding the surfactant or the amphiphilic molecules in pure water, the molecules, they first go over here in the aqueous bulk, but they prefer to absorb at the interface, thereby they reduce the interfacial tension. So you see, interfacial tension is represented with the E-flat lattice gamma. So as we increase the concentration of the surfactant, interfacial tension reduces. Eventually a point comes. After that, if you keep on increasing the concentration, then the surface tension becomes constant. The meaning for that is the interface is completely occupied, but whatsoever the surfactant or the surface active molecule you are still adding into the solution, they are going in the aqueous phase in the form of aggregates. These aggregates are known as micelles. In surface active or the surfactant chemistry, the aggregates of the molecule, those are being produced, we call them the micelles. And this one, the surface tension was the interfacial property, but likewise you need to know that what is the evidence for the micelle formation in the bulk. The bulk is the, in order to evaluate the bulk property, you can perform the conductivity. If you are dealing with the ion surfactant, so the conductivity is the most convenient technique which you can measure. Every college or high school, so they have the conductometric instrument. So first, in pure water, the pure water which is deionized water, the conductivity should be close to 0. It is usually in the 10⁻⁻⁶ range. But when you start adding the surfactant, conductivity starts increasing because you are creating ions. So these are the ions when you start adding the surfactant, and hence the electric current carrying ability in the water phase is by the ion. More and more ions are going to have the greater ability to carry the electric current, and hence the electric conductivity that increases. Eventually a point comes at a high concentration where you see a break. You see a high concentration, the high conductivity with a greater slope, and this portion is with a lower slope, smaller slope. It means the conductivity of this region, those species which were contributing towards the conductivity in this region, they were having the higher mobility to carry the electron density or the electric current. On the other hand, the species which are produced in this region, they are not carrying that much amount of electricity as much was being carried over here. So therefore, obviously, there is certainly a change in the solution property or the change in the species those have been created. So those you could see over here. When you have the single molecules, the single ions, those are present in the solution. Obviously, they have the greater dynamic mobility in the solution in comparison to the aggregated state, aggregated phase. So the aggregated spherical phase of the amphiphilic molecule, it faces greater viscous drag in comparison to that of the non-aggregated phase. So therefore, this aggregated phase, because it is also polar, carrying the positive charge if the surfactant is positively charged, negative charge if the surfactant is negatively charged. Right? They can also carry the electron, but their mobility in the aqueous phase is obviously much smaller in comparison to that of the monomeric phase of the molecules. So hence, the conductivity, the slope is less in comparison to the slope in the region before that. So this is, I mean to say that these two studies complementary explain the creation of, or the formation of the micelles. The most important thing over here is that we are going to talk about that how these micelles are required when we have to talk about the colloidal stability of the nanoparticle. How the micelle formation in the aqueous phase is a key to determine the stability of the nanoparticle in the aqueous phase. First, I'll take you to explain that what kind of micelles we are going to talk about. You see over here, molecules arranged in a sphere. But if we have a different kind of molecules, right, both are amphiphilic. You see the red and the blue? Both are amphiphilic molecules, but they have the different functional group. So they could be cationic, anionic, or they could be cationic, zwitterionic, they could be anionic, zwitterionic, cationic, non-anionic surfactant, anionic, non-anionic surfactant, any kind of combination we talk about over here. So having the different kind of combination, we call them the mixed micelle. This aggregate is known as micelle. So when it is of the single kind of a molecule, we call a simply micelle. But if the different kind of molecules are involved to create the micelle, we call it mixed micelle. And this is the example for the ionic and ionic, and this one is for the non-ionic and ionic. This one is non-ionic, though it has the head group as well, but it's not the polar head group the way we are showing for the ionic surfactant. So this is the mixed micelle for the combination of non-ionic and the ionic surfactant. What is the anatomy of a micelle? This is the anatomy of a micelle. I'm showing it in a much broader picture. You see over here, I'm talking about the same micelle. If somebody asks you, I can understand that the aggregates are formed. But I'm still confused that where is the polar part, where is the non-polar part, how the polar part is differentiated from the non-polar part, or what are the properties of the aggregate of the micelles as far as means in terms of the micelle water interface. So all those things, all those questions we can reply if we know the anatomy of the micelles correctly. So first I want that you simply focus your attention on the micelle. So I divided the micelle into different regions. This is the interfacial region. This interfacial region is known as stern layer. You see over here? Stern layer. We call it stern. The word stern is related to the scientist who explained this. So this stern layer is occupied by the head group, the polar head groups. Now you might be saying that if this is positive charge, how they can reside close to one enough in the stern layer or in the stern region, because they are having the identical charges, because identical charges we know they repel one another. So therefore identical charges are balanced by the counter ion. You see, this counter ion is oppositely charged. What is the meaning of this counter ion? This is the same bromide ion here we are talking about here. this bromide ion. Head group is this. So one head group arranged in the stern layer, another head group is arranged. This bromide ion is taking the space among them, so that this should not repel this another identical polar function. This oppositely charge is going to take the position over here. That is the thing which we have explained here. So all these white balls, white circles, you could see, so they are the counter ions. They could be bromide, chloride, or iodide. Now this stern layer is the polar region, and it means that the surface of the micelle, it's a kind of, suppose if you have to visualize that how the aggregate, or in 3 dimension, how can we visualize the micelle in 3 dimension? I'll say that simply you could see that it's a ball. It's a 3-dimensional ball. The surface of the ball is lined with the stern layer, and it is the polar, because it constitutes the polar function group, the polar head group, and the counter ions, and hence it is interacting with the water. So here it is the pure water molecules. So therefore the polar region of the micelle is in contact with the water atmospheres, and this is core. So core is entirely non-polar, because you see, as you move away from the head group towards the end, the non-polarity increases. So the first 2 methylene function group, those are connected to the ammonium head group. So they are still under the influence of the positive charge. But as you move away and away, the ability or the influence of the polar head group, that reduces, and hence you are entirely in the non-polar region. So that is why this is entirely a non-polar region. So contrastingly, the center is entirely non-polar, the surface is entirely polar. So therefore you can divide another 2. Now the second region is outer palisade layer. The outer palisade layer is predominantly influenced by the head groups. You see, this methylene group, this methylene group, this methylene group. So it means the first 2 methylene groups are completely influenced by the polar head group. So therefore they are still possessing certain amount of polarity, because they have the influence under the head groups. But when you are going over here, so then the effect of polarity is reduced dramatically. So this is the inner palisade layer, deep palisade layer, or the inner palisade layer, and this part is predominantly now non-polar, and this part is entirely non-polar. So in this way we divide the micelle into different portions, and I'm going to explain that what is the meaning for that, why we need to divide it, because micelle itself is a kind of a pot or a reaction vessel which has the ability to dissolve any kind of a molecule, no matter which polarity it is possessing. It has the ability to dissolve the polar component, because we have the outside the stern layer, that is polar. It has entirely a non-polar core, so therefore any hydrocarbon molecule which will otherwise be not solubilized in the pure aqueous phase. If you are going to put a drop of oil, you cannot solubilize, but if you put the drop of oil in a micellar solution, you can dissolve that. So that drop of oil is going to be accommodated in the core of the micelles. Mathematically, how can we quantitatively determine the characteristic properties of the micelle? The first one is the aggregation number. Aggregation number means how many monomeric molecules are arranged in a sphere to create a micelle. That is the aggregation number of the micelle. Radius of the micelle. You see, the radius of the micelle is, we have to start from the center all the way going to the surface. So it means that it is, I have not shown the end of the tail, but basically these tails are going to be extended exactly up to that. Suppose if you ask me, is it empty or the vacuum over here? I'll say no. This part is entirely non-polar, and it is occupied by the end of the tail. So therefore, the radius of the micelle is extending from here to here. Entire is the diameter, So it means that if you have to calculate the radius, obviously you need to know the length of the hydrocarbon tail plus the concentric area of the stern layer. So that is the radius of the stern layer, and that is the radius of the micelle. Volume of the micelle, because it is sphere. If you know the radius, it's 4 by 3 pi r cube. So radius, you know the radius, and you can calculate the volume of the micelle. Suppose if you ask me the conventional surfactant like sodium sulfate, what is the volume? I'll say it is very tiny, right? And maybe close to just few nanometer, right? 1 or 2 or even less, depending upon the tail length, right? And volume of the core. So you can also calculate the volume of the core, but the volume of the non-polar region, hydrophobic part. H stands for the non-polar or hydrophobic part. That is core for core as well as the palisade layer. So if you are having up to here and here, that is usually we include the outer palisade layer as well, right? So the non-polar portion extends from here to here. Predominantly these, I am simply talking about the length of the hydrocarbon, excluding this portion. From here to here, that is referring to the volume of the hydrophobic part of the micelle. Volume of the stern layer, so you know the volume of the micelle, the entire volume of the micelle subtracted by, and we can subtract the volume of the hydrophobic portion from the entire volume of the micelle, that will give you the volume of the stern layer. Volume of the tail you can calculate, this is the mathematical formulation. You can calculate the volume of the tail, that is 27.4, you don't need to go to formulation. 27.4 plus 26.9 multiplied by n stands for the number of hydrocarbon chains, and C the methylene groups minus 1. So you can also theoretically calculate the aggregation number. N stands for aggregation number, that is volume of the hydrophobic portion divided by the volume of the tail, and that would also give you the aggregation number. I mean to say that if you have the entire volume, and if you are going to divide the entire volume with only the volume of one tail, you will be able to calculate the aggregation number. How many tails are there in fact? Length of the tail 1.5 plus 1.26 multiplied by n. So as many methylene groups are there, so in this way you can calculate the length of the tail. So I mean to say that these are the characteristic properties of the micelle. Okay, so just a minute, let me see how many. Okay, yeah. So now somebody can ask you, are we expecting the micelles always existing in the spherical shape? No, that is not. But the initial aggregation, when we increase the concentration of the surface active molecule, that takes place in the aggregated or spherical state. If we keep on increasing the concentration, we transform the shape from the sphere to the cylindrical micelle, and then if we keep on further increase the concentration, it becomes a plate-like micelle. So I'll show the images for that. So here is the definitions for the different parts. So this is the head group surface area. We call the surface area S. This is the volume, overall volume, and this is the length of the hydrocarbon portion. So surface area we know 4 pi L square. We have already defined L in the previous, and the volume is 4 by 3 L cube. And hence we can say N multiplied by the volume. Here we are talking about the volume of a single molecule, or the hydrocarbon chain for the molecule. So if we divide V by Ls, so it is 1 by 3. So this is the surface area for that of the spherical micelle. Likewise, this is 1 by 2 for the cylindrical, and it's 1 for that of the plate-like micelles. These are the theoretical considerations. Somebody can ask you, can you show me actually in an image where are the spherical micelles? Is there any way to see them in an actual image? Yes, we can see them in the actual image. But first I'm going to tell you that how this transformation happens. We first deal in the aqueous solution when the concentration is very low. The molecules exist in a single species, that is a monomeric form. We call them monomers. By increasing concentration, we convert them to aggregates of spheres. Further increasing them, it's a rod or thread-like structure. Further increasing them, we produce the vesicles. The vesicles are the same which we talk about in biology. And you could see over here, in this case, this entire transformation is happening in the aqueous phase. The aqueous phase is over here, and the head groups are in contact with the aqueous phase. What if we talk about in a non-aqueous phase? It means that in non-aqueous phase, the tails have to be oriented towards the non-aqueous phase. What kind of non-aqueous phase? Somebody can ask you, what if we replace water with hexane? Are we still expecting the same kind of aggregates? We can expect the same kind of aggregate, but then the shape is inverted. You see, this is the reverse. Here the head groups are towards the aqueous phase. So when I'm going to replace the aqueous phase with the hexane, then the head groups cannot interact with the hexane, and then the shape is inverted. Then the tails they are hydrocarbon non-polar, they are going to interact with the hexane. So that's why we call them the reverse micelles. Reverse micelle. And so the same is the story for the lamellar structure here. As you see in the rod-like, thread-like micelle, head groups are in contact with water, and here, if hexane, the tails are in contact with water. So this is the way transformation helps. You need all this information. Why we are going through this aspect, which has a little relevance to the nanoparticle synthesis, but that is not the thing. When you have to properly produce the stable nanoparticle suspension, you need the knowledge of everything. Only then you can generate the stable suspension. Okay, here is the transmission electron microscopic image. You see the dots, black dots? These black dots are in fact the micelles. And what are the dimensions? This is 100 nanometer. And you could see that if I have to split the scale bar to here half, this is the 50 nanometer, further half 25, further half close to 12 nanometer, further half 6 nanometer, 3 and close to 1. So practically the size of the micelle is close to 1 or 2 nanometer only, right? So these dark dots, they show the nanometer. What are the elongated micelles? Thread-like micelles, which I was talking about over here. Yes, when the micelles, they merge with one another, they produce the thread. You see the thread over here? Thread. So if we keep on increasing the concentration, more threads and longer threads are generated. You see the threads over here? So they are the longer thread. It means that more and more micelles are going to fuse with one another to produce the longer threads, right? And if I further keep on increasing, then at some point the bilayers are produced, and eventually those bilayers are converting. I mean to say that it is basically the threads are now in much elongated state. So here you may not be able to see the bilayers, but they are now, they have produced the bilayers. Since the threads in fact are the bilayers, and now eventually the bilayers are going to merge, or the threads are going to, threads, if I have a thread, and if I connect the end of the thread, or merge the thread, I can produce a circle, that is vesicle. So I mean to say that the vesicle, what is vesicle here? If I have a thread, longer thread, and if I join the ends of the thread, I can make. Let me have a colloidal particle. This is a colloidal particle, okay? So it could be a gold particle, you may say a silver particle or anything like that. So surfactant is going to adsorb at the surface. The head groups are arranged like this, and the water molecules are here. So they are all water molecules. Tails cannot stay in water, so therefore there is another layer. This is the bilayer. You see, this bilayer, I can say it is the bilayer that is coating the nanoparticle. This is nanoparticle, gold nanoparticle you see, right? And this coating or the bilayer, which is coating the surface of the nanoparticle, is providing the colloidal stability. The bottom line is that what should be the concentration? In order to establish the bilayer, what should be the concentration? The whole fundamentals of the surfactant chemistry I have explained over here, just to arrive at that what concentration we should choose. We should choose the concentration of the surfactant which is much higher than the concentration where the micelles are formed. What is that concentration? So as you see that in connectivity experiment, this is the concentration, we call it critical micelle concentration when micelles are produced. It means that if I have to stabilize the nanoparticle, the concentration of the critical micelle concentration of SDS, CMC of sodium dodecyl sulfate is 8 millimolar. Use SDS to create the bilayer to stabilize the nanoparticle, then I would prefer to have at least close to 5 to 10 times the concentration than that of the 8 millimolar. Right? Minimum I should keep, from my experience, I would prefer to keep the concentration much higher than that of the critical micellar concentration. How that helps to create the bilayer? The reason is now, if I am creating this, it means that I have already micelles in the solution. So I have micelles of SDS in the solution. The presence of micelle in the solution confirms that all interfaces are occupied. Do you agree with this statement? The presence of the micelle beyond this concentration confirms that all interfaces are occupied. Why? You see, the micelles only form when all interfaces, the one over here, other one over here, other one over here, which I am not showing, so they are all occupied. Only then the micelles are going to be created. So it means that if I want to coat the nanoparticle, I must ensure that the solution phase should possess only the micelles, means predominant amount of the micelles, so that that would ensure the occupation or the passivation of all interfaces, including the interface solid liquid interface that is of the nanoparticle. That is why this is required. But so that was the part related to the colloidal stability. If you ask me, then why we need to understand the different kinds of shapes of the molecule over here, how they are related to the nanoparticle stabilization. They are in fact related to the crystallization of the nanoparticle in the surfactant solution. So I'll explain that, I think tomorrow probably, because we have to deal further. In the second lecture, I'll be dealing with some of the characteristic thermodynamic quantitative properties of the micellar solution. So okay, so I'm going to finish it over here, and in conclusion, surface active molecules, we have already talked about what is the definition of the surface active molecule, head group and the hydrophobic tail modification. Modification means you can increase the tail length, you can have double tails, you can change the head group from monomeric to the dimeric, and then we have talked about the anatomy of the micelle. The anatomy of the micelle helps us to understand that which part of the micelle is polar and which part is non-polar. Thank you so much for your attention. Any question, please? Before going, so again, just reminding you that we have tried to understand the characteristic properties of the amphiphilic molecule. Those are surface active, surfactant, their aggregation behavior. Now we will go ahead with the quantification. Quantification of the bulk and the interfacial properties. Quantification means how we can measure different characteristic properties of the aggregated phase. Among them, the first one is the stability of the micelles. Remember, we talked about the stability of the nanoparticle in yesterday's lecture. So this time we are going to talk about the stability of the micelle. You have to keep in your mind that stable micelles are the most important entities to produce the stable colloidal solution. So we have to have the stable surfactant structure which produce stable micelles. So I'll explain what is the meaning of the stability here. But how we can determine the stability? So stability we determined in terms of free energy. You all know what is the definition of the free energy and how we can evaluate the free energy of the micelle formation. We begin with the chemical potential. Chemical potential of the surface active molecule in the micellar state, that is mu. Under standard state condition, that is the naught as superscript. M stands for the micelle as subscript. The chemical potential of the surfactant in the micelle is equal to the chemical potential in the monomeric form. This one stands for one molecule. Monomeric form in the standard state plus RT, gas constant, absolute temperature multiplied by ln, natural law, activity. You know that what is the meaning of the activity. Activity is related to the activity coefficient and concentration. If you go through the physical chemistry and there in thermodynamics, you will be able to understand what is the definition of activity. So here we are talking about the activity of the surfactant molecule or the surface active molecule. If I rearrange this equation, take this mu1 on the right hand side, so the difference in the chemical potential in the micellar state to that of the monomeric state and the micellar state, I mean to say that which states we are talking about. So I'm saying that this is the monomeric state of the micelle where you have only the surfactants in the monomeric form, and these are the micelles. Okay, so you have the chemical potential is standard state 1. You have the chemical potential of the surface active in mu. This is mu in the micellar state. So the chemical potential in the micellar state minus that in the monomeric state, that is the standard free energy of the micelle formation. So it is the difference between the chemical potential between the monomeric and the micellar state. That is the definition of the standard state free energy change for the micelle formation. You know the definition of the free energy. So the spontaneous process should possess negative delta G and or the zero. If the spontaneity or the delta G value is zero or negative, it means that the process is spontaneous. We will try to understand that in what circumstances the micelle formation is a spontaneous process. So therefore we are expecting to achieve delta G negative. So delta G micelle formation standard state RT ln X. Here the activity is replaced with the mole fraction of the surfactant in the micellar state. So in the micellar state, the mole fraction of the surfactant is equated with the CMC, critical micellar concentration, CMC divided by 55.5 moles of water, right? So you can simply substitute that value of X with the X CMC and further rearrange it. And now it is delta G micelle formation, that is RT ln X CMC. What is the meaning for this? I mean to say that if you substitute this value, you take the CMC, divide this by 55.5. CMC you can determine from the conductivity or the surface tension. Divide this by 55.5, take the natural log, multiplied by the temperature at which the experiment has been performed in Kelvin, multiplied by the gas constant, and you will have the delta G of the micelle formation. You can directly calculate the value. Under what circumstances this value could be negative? Actually, the standard state micelle formation is the contribution from the hydrophobic component and the polar component. So it means that, what is the meaning for this? The meaning for this is that the contribution for the delta G formation is originating from the contribution of delta G of the hydrophobic. HP represents the non-polar part and delta G S is the polar part. If I add these two, so I have delta G of micelle formation. So therefore I can split the uh, micelle formation free energy into the contribution of hydrophobic free energy contribution and the hydrophilic free energy contribution. You could see here I have defined due to the hydrophobic interaction and due to the electrostatic interaction. When the micelle is formed, uh, the hydrophobic interactions are here. So this is the hydrophobic interactions between head group and head group. So it is delta G HP. And these interactions between polar and polar, that is delta G, the polar interaction. You know that in order to create a micelle, a aggregate, I need to minimize the repulsion between positive and the positive charge, and I should enhance the attraction between non-polar and non-polar. So if you look at the structure of the micelle like this, if I have to place another one over here, and the longer the non-polar part, the stronger are the interaction. Stronger are the attractive interaction, right? And if the polarity is enhanced over here, the greater are the repulsions, right? So I have to minimize the repulsions to have the compact arrangement, and I have to enhance the active interaction that leads to the stable micelle formation, right? How do I know that? In what way I can? There are ways to create the stability. If I increase the length of the hydrocarbon, the van der Waals interactions, non-polar interaction will enhance, and in this way, the micelle is going to be stabilized. If I reduce the polarity, thereby I am reducing the repulsive interactions, and hence the head group will be lying closer to one another, and this way the micelle is going to be stabilized. So, what is the spontaneous process? Now it is the contribution of these two. In order to make the delta G negative, you see the negative sign over here, I need to increase the attractive interaction of the hydrophobic contribution. So increasing the hydrophobic contribution will make the change spontaneous. So this is a negative contribution of the hydrophobic, I mean to say that it enhances the spontaneity. So that is referring to the negative sign, right? On the contrary, the delta G becomes positive when there are stronger repulsive interaction between the head group. So these head groups, those are being provided by the delta G S, that is the hydrophilic contribution, right? So in order to achieve the negative free energy of micelle formation, hydrophobic contribution in comparison to that of the hydrophilic contribution. Hydrophilic contribution is contrary to the micelle stability. So its delta G formation is positive. Hydrophobic contribution is enhancing the stability. So therefore its contribution is negative. So you have to enhance the negative contribution in comparison to the repulsive contribution contributed by the polar head group. So those factors which will enhance the non-polar interaction and reduce the repulsive interaction will automatically make the delta geomycin formation negative and the process will be spontaneous. That is the meaning of this whole story. So suppose if you ask me, when the micelle formation take place, so here when the micelle formation takes place from the monomeric to the micelle, it is spontaneous, so the delta G is always negative, right? If the delta G is positive, there will not be any micelle formation. In other words, I'm going to say that if there are strong repulsive interaction, we cannot place the molecule in a kind of an aggregate. So the resulting delta G will become positive. So therefore, we have to reduce this repulsive interaction to have the micelle formation, and those surface active molecules which produce micelle, they have always the hydrophobic contribution is much more enhanced in comparison to the hydrophilic contribution. So that is the meaning of this whole story. Suppose if you ask me, if you are not working in this project or in this kind of a project or a direction, you may think it is completely a theoretical, but there are ways to calculate delta G. I mean to say that if you measure the CMC, as I've told you in the previous lecture, that you can measure it from the conductivity or from the surface tension by first measuring the CMC, and then you are substituting the value over here, calculating delta G, and then you can split the delta G into different contribution. So there are ways to calculate quantitatively the hydrophobic and hydrophilic contribution. Uh, Another quantitative is slightly more intensive mathematical expression. So we are picking the same equation, the one I'm saying over here. It's the same equation where we have picked over here, right? And what we have done, so the delta G micelle formation contribution is coming from the terminal methyl group. So here is the terminal methyl group of the hydrocarbon chain plus M or the N number of methylene group, and there are, if there are 12, so you have one terminal, 11 are left, so it means that the value of M is 11. The contribution of each of the methylene group is delta Gm multiplied by M plus the contribution of the delta G from the head group region. This W stand for the head group region, right? And all these contributions, and from the solubility of alkanes, we can have the contribution of the terminal methyl group. We can convert into the methylene group, and we can substitute this, and the entire formulation is now in the methylene group. So we have two parts now. The equation, this top equation now have taken the form of this because I've substituted the value of delta G in this equation and rearrange it in this form. So suppose if you ask me how we have done it, you can easily do it at home. You simply rearrange the equation. First you you see the log. So first what you can do, here it is ln. The first thing you will be doing, you are converting ln into log. You know how you can do it, right? And then eventually you are going to get equation. And then the delta Gm contribution is given by this entire terminal and methylene groups and the head group region. You are going to substitute the value of this delta G terminal from here in this equation, and this equation then you are going to insert it over here, and this is the resulting equation. You can do it by yourself. There is no difficult mathematics involved in this case. You are going to split this portion into two parts. This part of the equation up to here is, you can label it A, other one is B. I'm going to explain what is the meaning of this, multiplied by the value of N. So N is the same which we talked about in the previous lecture, aggregation number. If you have the CMC, log of CMC, if you are going to plot the CMC from different surfactants with different value of N. Obviously, if you are going to choose different surfactants, all the aggregates having the different value of the N, that is the aggregation number. So all different surfactants having the different CMC. If you are going to plot the log CMC against N, this is the slope part, slope is B. This is the intercept, intercept is A, right? So you can calculate the value of A and B from the intercept and from the slope. And now how it is going to help us? The A value, from the A value, you can substitute the gas constant, temperature, take the log of 55.5. Eventually, you will be able to calculate the head group contribution. This is the head group contribution. By equating the entire term with A, you can calculate the delta G for the head group contribution. By equating the entire term, the second term with B, B you have already calculated from the slope, you can calculate the delta G of methylene contribution. So I mean to say, this is the way we can have these two contributions, right? If you want to have the contribution, hydrophobic contribution, the hydrophilic contribution, this is the way you can do it. So I mean to say that this is, in fact, it's a slightly intense theoretical characteristic properties to calculate, to evaluate for the CMC of the different surfactant. Probably you may not need it, but I just wanted to tell you that this is the way we can quantify. Okay, so apart from the delta G, we have other thermodynamic parameter. So you can calculate delta S as well, right? And when delta H, that is enthalpy, is constant over a temperature range, so you can calculate the entropy of the micelle formation. You can also calculate the enthalpy of the micelle formation. You have calculated delta G. From the delta G, you can calculate the delta S, entropy of the micelle formation, and the enthalpy of micelle formation. So this is all about the quantification in physical chemistry or in thermodynamics term, right? So I just wanted to let you know that this is one way of determining that how much micelle is stable, delta G. Now we are coming back to our previous story. Remember I told you the anatomy of the micelle, and I told you the different parts, and I told you that the micelle is in fact a single pot, and this single pot has the ability to dissolve all kinds of molecules ranging from the non-polar to all the way to the polar. How we can do it? So this part is entirely polar. The polar part is slowly converting into the non-polar part as you move from the surface to the center. It means that this is entirely polar, predominantly polar, less predominantly polar, and entirely non-polar. Okay, if that is the story, so how can we solubilization in the micellar phase? How can we pick the sites for the solubilization of the different species? So I'm going to explain what is the meaning for that. Uh, just a minute. So you already know that what is hydrophobicity, that is the hydrocarbon chain length. We can increase the hydrophobicity, non-polarity of the micelle by increasing the chain length from here to here. Hydrophilicity can be increased by having the stronger polarity, this one in comparison to this one. Branching, unsaturation or the saturation, here you could, because here I've shown you only the normal hydrocarbon chain. So you can have the, here it is completely saturated. There is no the hydrocarbon chain with the unsaturation, that is the double bond. But keep in your mind, by adding the unsaturation, so the hydrophobicity, the non-polar ability of the micelle, that reduces, because the unsaturation is some degree of polarity that you are going to introduce. So therefore, means suppose if you want to have entirely a non-polar micellar core, it means that you have to avoid the unsaturation. So head group modification, you see here, this is sodium dodecylsulfate, SO4 oxygen. Here it is triphenyl phosphanium, this phenyl. This one is butyl, this one is methyl, and this way. So I mean to say that you can change the head group modification, and obviously when you have the oxygen, so the polarity is going to be affected. When the negative charge is on the terminal functional group connected to the central atom, and in comparison to when the charge is on the central atom of the head group, so there's a difference in the intensity of the charge. So that also changes the ability with which the charged portion is going to interact with the other charged portion. Suppose if you have to solubilize the ionic compound in a micelle, ionic compound or any polar component, or any polar solute you solubilize in the micelle, that will be solubilized in the stern layer. Stern layer is polar, so the polar portion is going to be absorbed in the stern layer, right? So here AB represents the salt. The negatively charged ions are going to be adsorbed on the interface that enhances the stability or the solubility of the electrolyte. So electrolytes can be solubilized in the microphase solution. Polar covalent compound, alcohol, ethers, and esters can be solubilized. They are not entirely polar. Like I suppose if I say the propanol, butanol, pentanol, or hexanol, they are not entirely polar, right? How they are going to be solubilized? Suppose if someone asks you, I understand that this is the micelle, right? But the question is, if this is the micelle, and if I am dealing with the alcohol, OH, right? Pentanol, you can say C5. I can represent it just like that of a surfactant molecule. How it is going to be solubilized? I'll be saying that this is OH now. So OH will be over here. OH has to be here because this is the polar region. This is the polar region. OH is going to interact electrostatically. OH is having the dipole, so it is going to interact with the positively charged head group, whereas the CH5 is a shorter tail in comparison to C12. It will be closer to the non-polar region. So therefore, this is the way the solubilization is occurring for all of them. Alcohols, higher alcohols, ethers, and esters. The polar functional groups of these molecules will be closer to the stern layer. The non-polar will be closer to the non-polar part. If you are dealing with entirely hydrocarbons, hydrocarbons are completely non-polar. The solubilization of the non-polar is going to be in the core. The core is entirely non-polar, so therefore the hydrocarbons are going to be solubilized in the non-polar region. What if we are dealing with the solubilization of the polymer? So here we have different kinds of polymer, neutral polymer, polyelectrolytes. Like here you can say that if we have the polymer, right, and in the polymer you have the side chain, so then the polymer is going to wrap the micelle. It is going to wrap the micelle like this. The polymer without the side chain is again going to wrap it like this. So it means that it's not just one micelle that is going to associate with the polymer. Number of micelles are going to associate with the polymeric molecule. Now, if the polymer is having longer hydrophobic functional group, so this is the longer hydrophobic portion of the functional group of the polymer molecule. So it will try to fold and enter into the palisade layer, right, in order to entrap the micelle. What if we are dealing with a polyelectrolyte? This is the anionic polyelectrolyte. Anionic functions are repeating in the polymer backbone. This is cationic polyelectrolyte. The positive charge is repeating on the polymeric backbone, right? And then, depending upon the charge on the micelle, they are going to be absorbed at that portion. If the micelle is negatively charged, it is going to take this position, as you could see over here. And there are two ways then, because the micelle is positively charged, so the monomers are also positively charged, right? So then the monomers are first going to interact with that of the active sites, oppositely charged sites. You see the monomers attracting, you see the micelles are attracting. So suppose if you ask me, what could be the conductivity behavior in that case when we are dealing with the polyelectrolyte, or we're dealing with the ionic or the cationic surfactant. So as we start adding the surfactant, cationic or anionic surfactant in the polymer solution, the conductivity increases slowly, and you will see the first break. The first break belongs to this kind of aggregation where monomers are going to interact with the active sites. We call it critical aggregation concentration. It is not the critical micelle formation. When these positions are occupied by the monomeric molecule, we are still increasing the concentration of the surfactant. Eventually, they will take the turn into the micelle because you have to accommodate more surfactant. So therefore, the monomers will aggregate at the same pocket positions in the form of the aggregate, and you have now CMC over here. So the actual CMC of the surfactant in the presence of polymer is over here. The first break is the critical aggregation concentration. So you can show it like this. The critical aggregation concentration, it obviously when you have just the monomeric form associated with this, right? When the sites are occupied, if you keep on increasing the concentration, eventually these all sites are occupied by either the monomers or the micelles, and then you will see the free micelles of the surfactant. And so therefore CAC arrives before the CMC. CAC must be a must. You will see the CAC before the CMC. So CMC is only when all the active sites of the polymer are occupied, and then the added surfactants, so they are going to be in the aggregated states of the micelle. Now, what is the purpose of this information? The purpose of this information is that I'm taking you to slowly to the bioapplicability. The purpose of this information is because there are plenty of products in the cosmetic industry or in other pharmaceutical industry where you have the micellar systems in action. How? I'm going to explain that. First, I'm going to take the most common examples, the applicability of the surfactants. We talk about the the cleaning action in the previous lecture, that how the soap particles are removed or the clothes can be cleaned. In terms of the free energy, you need to make the dissolution of the oily particle spontaneous. It means this process must be spontaneous. Spontaneous process means this delta G should be 0 or negative. Where are the interfacial tension existing? This is the interface between gamma represent the Greek letter for the interfacial property, uh, uh, interfacial tension between oil and water. So you have a oil and water. So exactly at the surface tension that exists, that is gamma of W. Oil and solid. So the surface tension that exists, interfacial tension exists over here, that is the solid and the oil. Surface and water. The solid surface and water interfacial tension exists over here, that the gamma, solid and water interfacial tension. How to make this spontaneous? So it means that delta G of the cleaning action when your washing machine runs, there are three contributions. The one is the interfacial tension between water and oil, solid and water, and solid and oil. This term is negative, the other two are the positive. So in order to make delta G 0 or negative, you have to have this term predominantly higher than the summation of these two terms, right? So now you see that, what are these terms? So solid oil, the solid oil over the binding force, which is keeping the sticking the oil particle to that of your cloth or any surface. So this has to be removed, right? So this you are going to remove only when you are going to enhance the surface activity by putting the surfactant. So the surface activity here, you cannot simply means there is no way you can merge the, or you can I'll say introduce the surfactant molecules over here. There is no place, but you can reduce the surface tension of these two components by adding the surfactant. The surface tension of oil water is reduced. The surface tension of solid water is reduced by putting the surfactant. Thereby, the magnitude of the solid oil is automatically going to be increased. And thereby, we are going to have the delta G negative or 0, and hence the process is going to be spontaneous. This is the cleaning action. This is the most prominent example of surface active molecule and surfactant. Where are the biological applications? We are now going ahead with the biological applications. So the first one is the cosmetic cleaning. So you every day you use the lotions, right? And here is your outermost, right? And you have mainly the dead cells, we call the horny layer, right? What you do in order to reduce the amount of the dead cells, you have the coating of emulsion. Usually the lotion is an emulsion. It is made up of the combination of oil and water. Oil and water you cannot mix. Then how you created the emulsion? Without adding the surfactant, you cannot create the emulsion. The surface active molecule is going to create the or going to help the mixing of the oil and water. So what that emulsion which you have, or the lotions you have, you are going to coat it like this. This will act as a layer that will reduce the evaporation of water, keep the moisturing of the skin. This is another most important property of the surface active molecule. So what is emulsion? Emulsion is exactly the combination of oil and water, which your lotion is made up of. Oil, this black ball is representing oil, and the water is the blue shell, and the surfactant surface active molecule is binding these two faces, creating the lotion. And that lotion, when you are going to use, that is going to prevent the unnecessary evaporation from the skin, keeping it moist. Next one is entirely related to the human health. Human health, respiratory system. How the surface active molecules help us achieve that. Your lungs, in fact, they are working only because of the presence of lung surfactant. The lung surfactant, they are lining the alveoli. So you have alveoli, so you have the lining over here. That lining is created by the biological surfactant. So it is not those conventional surfactant which you are using in your laundry or in the soaping in your washing machine. These are the surfactant produced by the human body by itself, and we call them the biological surfactant, the lung surfactant. And they line all the alveoli. This is the air exchange. Air exchange is taking place. So these particles, you see that, so they are the air particles. So that exchange is taking place on the surface of the alveoli, right? You know that we are talking and we are breathing, and without even sensing that we breathe. The reason is that because it is an automatic process, the nature has provided us the automatic process. Lung contracts and expands. Now, lung itself is a human flesh, and most of that part is in aqueous environment. So therefore, what kind of this interface is? This interface is predominantly aqueous phase and air phase, because the human body is predominantly made up of aqueous phase. So suppose if somebody asks you that since the surface active molecules are lining the alveoli, then they have to be at the interface. And which interface we are talking about? You will be saying that it is the interface between the aqueous phase and the air phase, not the solid phase. In the human body, except the bone, there is no solid phase at all, right? Okay. Now, what is the participation of the surfactant here? Uh, so we started, uh, I think I have to finish it, 11, no, 12? 12, 15. Okay, I have to 20 minutes, sorry. Yeah, okay. So, uh, the film of the surfactant, biological surfactant that lines the alveolus, that is very, very important. So, anybody who's so having the lung problem, that could be because of the pollution or any other reason. So this film is not continuous. This film is not continuous. I have also the same problem, and because after the vaccination, I have to keep the inhaler because the vaccination so somehow my that biological surfactant concentration film, its concentration changed. I don't know what is the reason. Many of the people in North America, in Canada and USA having the same problem. So slowly, the effect is going to diminish after 3 years, and I am feeling much more now better. Earlier, I had a very severe problem. Means it was not possible for me to even continuously talk for 1 hour. So I had to stop in between to drink water and then to speak. But now the situation has improved quite a lot, and I am continuing taking the lecture 1 hour, and there is no issue. So I mean to say that if you have a problem related to respiration, it means that something is wrong with the biological surfactant lining, right? And you could say acute respiratory distress syndrome in biology or medical term. So these terms are related to the fact that something is wrong with the layer of the biological surfactant that lines your lung. So it could lead to very serious consequences that if it is sometime if it is too severe, now obviously it could lead to the fatal circumstances, because it is obviously it is a respiratory system, and if your respiratory system is going to collapse, no one will protect you, right? So now in high resolution, what is happening? So this is the high resolution image, right? Is a schematic region. Suppose if somebody asks you from where this, you see, it is the bilayer, exactly the bilayer which I was talking over here. The bilayer means, as I told you, that on the surface of the nanoparticle, this is nanoparticle, and this is the surfactant. Another surfactant is going to arrange like this. This is the bilayer, right? So the same bilayer, this bilayer, this is the bilayer over here. This bilayer runs on everybody's alveolus. Every alveolus in lung is lined with the bilayer. Okay, how this bilayer is produced? What nature has provided us? These are the bilayer is produced by you see these small vesicles. The vesicles are produced by type 2 epithelial cells here in the cell. These vesicles are released. You see they are released from the cell. They go at the interface and convert into bilayer. We talk about the micelle shape transformation. So we talk about the spherical micelle change to rod shape micelle, rod shape micelle change to bilayer, bilayer then convert into the vesicle. If you trace the process in the backward direction, that is happening over here. So you have the vesicle unfold, break down, and they form the bilayer at the interface. So it means that this is air fluid interface. Air fluid. Here it is the aqueous phase, and here you have the air exchange take place because it's empty, alveolus is empty, there is air inside, so that is the interface over here. For a normal person, this is a continuous bilayer. For those people who don't have any problem with their respiration, they have continuous bilayer. And I'm talking to you, you putting the attention without knowing that your respiration is working. Your lung is contracting and expanding because you don't have who has the respiratory problem, pressure on the lung to expel the air, bring the air inside. So what happens when there is a problem? We call it injured lung for any reason. It could happen because of the pollution, right? So suppose if you imagine the pollutants are coming over here, or the way in most of the cases we have in North America now, this COVID vaccine side effect, and that what is affecting? It means that the COVID vaccine effect is somehow affecting this vesicle formation. If there is no sufficient amount of the vesicle formation, it means that there is a problem. This is not a continuous one. You see the broken bilayer? This broken bilayer cannot provide the sufficient amount of surface activity. If there is not a sufficient amount of surface activity, the contraction is not complete. The lung cannot completely contract to expel all the amount of the air. So there is a partial contraction. The partial contraction is the problem for the respiration. Okay, so just a minute. Yeah, okay, just a minute. What are the other slides? Yes. Okay, so now somebody can ask you that what is the composition of this surfactant? Which surfactant we are talking about? I have explained the chemical structure of the different surfactants. Ammonium salts, phosphonium salts, you have seen the ether derivatized surfactant, and so many more. But what kind of these biological surfactants are? You have to keep in your mind the biological surfactants are the schematically the structure is the same. They also have the hydrocarbon chain as well as the head group, but chemically functional group is creating the head group, polar head group for the biological surfactant, and which one for the hydrocarbon chain. And then we have here. These are the biological surfactant. Phospholipids are the biological surfactants. Among them, we have the combination of 70 to 30%, 70% DPPC, 1,2-dipalmitoyl SN-glycerol 3-phosphocholine. This is 70% composition, and POPG. So here are the name for different POPG, DMPG. POPG means it is C16 to C18 combination, and DMPG it is C14, and DPPG is C16. So all these are some of the sodium salt, or they may or may not be the sodium salt, but the sodium salts are highly water soluble, so we can solubilize them. So usually they are in the zwitterionic state. So you see over here. So this one is cationic, right? And no, zwitterionic, cationic. You see the positive charge and the negative charge. This one is in the salt formation. You have the sodium salt over here. So these are the polymerase surfactant. We call the polymerase surfactant. So the 90% of the phospholipids are the combination of DPPC and POPG. But plus then you have the 10% of the surfactant proteins. Which surfactant proteins? You see the you are familiar with the proteins, but you see why I have used the word surfactant. So we can attach, means how we can say the protein acts as a surfactant. If a protein molecule is surface active, protein is a polymer. It's made up of amino acids, you know already, right? But we call it a surfactant protein. So not all proteins are surface active. You have to keep in mind. So albumin proteins, so they are not surface active, right? But some specific proteins which are being produced in the lung, so they are the surface active proteins. And you have three, four SPA, B, C, and D. These two, they are hydrophilic, predominantly hydrophilic surfactant proteins, and SPB and SPC, so they are the hydrophobic surfactant proteins. So I mean to say that, so I'm going to conclude it over here. This is the first bioapplicability we have talked about. This bioapplicability is, you have seen the difference. This bioapplicability without nano. But the main purpose is we are slowly arriving at the bioapplicability of the nanoparticle. But before arriving to that, because nanoparticles are coated with surfactant, you need to understand that how the surfactants are having the role played in the bioapplicability, and to understand the role of the surfactant in biological application, the best way to demonstrate that is the surface activity of the biological surfactant in your respiratory system. So finally, I must conclude the two lectures, because today's lecture were on the surface active molecules, their characteristic properties, their chemical structure, their non-polar and the polar functional group, and what kind of polar and non-polar functional group constitute surfactant molecules. There are different kinds of surfactant molecules: cationic, anionic, zwitterionic, and non-ionic surfactant molecules. And then we talk about their aggregation process. They are not conventional molecule. I mean to say that if you keep on increasing the concentration of sugar in water, you're not expecting to form the spherical particle like micelles. Sugar molecules are not going to arrange themselves in the spherical aggregate. The same is the story for sodium chloride. If you keep on increasing the concentration of sodium chloride in water, you are not going to have a specific aggregates the way you see the surface active molecule. Then what prompts, what drives the aggregation process in the specific spherical shape? It is the dual behavior, the dual functionality of the molecule. As long as the molecule is not possessing the two functional group, the one interacts simultaneously with the polar and the other one simultaneously with the non-polar, there is no way you can have a specific aggregates the way the surface active molecules produced in the aqueous phase. Sugar molecule, sugar molecule is not possessing predominantly hydrophobic phobic region. Sugar is highly water soluble, right? So because of its hydroxyl group and all other functional groups. And likewise, the sodium chloride is ionic, and practically there is negligible amount of the non-ionic character. So therefore, it's a highly ionic, it's a strong electrolyte, it will instantaneously solubilize in water, and there is no question of a specific aggregate formation at a particular concentration. But the specific aggregate formation at a particular concentration is only and only property of the surface active molecules, and we have demonstrated that. So I told you that the conductivity and surface tension are the most conventional or the convenient ways to evaluate that if a molecule is surface active or a surfactant or not, where the micelles can be formed or not. Then we talk about the anatomy of the atom. Cell, to just understand that if we have to use it for the solubilization process and how we can solubilize that. The relevance of that discussion was when you are putting the soap in the washing machine, so you have to have micelles. You have to take a big spoon of the surf or any soap, and you have to put it in the washing machine. That has sufficiently much higher concentration than the total volume of the water you are going to take, concentration than the micelles, CMC. So it means that the volume of the water you are taking in the washing machine and you are putting 1 teaspoon of the powdered soap, so that will certainly produce a micellar solution. And that micellar solution has ability. It's not always the soap your dirty clothes are having. So it is the what we say those uh, ਉਹ ਜੋ ਸਮੋਸਿਆਂ ਤੇ ਪਾ ਕੇ ਖਾਂਦੇ ਮੈਂ ਭੁੱਲ ਗਿਆ ਕੀ ਕਹਿੰਦੇ ਆ ketchup and all those stuff, so that is water soluble. So those are containing polar components, oil containing the non-polar components. So everything is solubilized because micelles are there, and you have learned that the mice can solubilize everything. So that is the reason when in your washing machines micelles are there, no matter the dirt which is or the dirty clothes, those are being created by the polar or the non-polar dirt particle. They are all going to be solubilized by the micelle. Then we shift to slowly the thermodynamic properties. If you want to have the quantity information, stability of the micelle, we talk about that. In order to have the stable micelles are required. I told you to have the proper bilayer around a nanoparticle, right? And the stable micelles will produce stable colloidal solution that we will talk about in next lectures. So stable micelles, quantitatively, how can we calculate? We can calculate when we have the stronger hydrophobic contribution of the free energy that will help us to create the stable micelle formation. Eventually, we have gone to slowly to the cleaning process, mechanism of the cleaning process, and that of the biological application. And this is the first biological application that will help us to understand the bioapplicability of our nanoparticle. And you see, today we have completed 4 lectures, but we have not yet arrived at the iron oxide nanoparticle. I do not want to take you directly to the iron oxide nanoparticle. The reason is that you are more familiar with the gold or the silver nanoparticle. So therefore, first you need to understand the behavior of those nanoparticles. If you are clear about the behavior of those nanoparticle, and then you will not be having any much problem in understanding the behavior of iron oxide nanoparticle. And eventually, so I'll be taking you to iron oxide nanoparticle, synthesis, stabilization, and then their bioapplicability. Thank you so much for your attention. Any question, please?
Parameters for the bilayer monomer micelles.
Yeah, so bilayer is in fact, you are saying that the bilayer, the thread-like micelle, rod-like micelle, which you are, yes, absolutely, you are correct. Actually, the thing is that whatsoever the treatment you are applying to, the aggregated state, micelle, spherical micelle is the first aggregated state that is being produced from the monomer to that of the micellar state. But the rod shape or the bilayer is the transformation of the micelle. No aggregation is means the kind of aggregations you have expected from the monomer to the micellar state. That kind of aggregation is not occurring. It is simply the structure transformation of the sphere to rod, rod to ribbon, ribbon to vesicle. It's so therefore it's a structure transmission. But the actual thermodynamic treatment which we have talked about over here, that is applicable to the micelle, right? So first we will apply to the micelle, and then we talk about the stability of the micelle further when it's going to undergo the shape transformation from the sphere to a rod or thread. Okay, thank you so much. See you next time.
So now in this tutorial we will have hands-on synthesis regarding the Gemini surfactant, and this particular tutorial is in alignment with the lecture number 3 and 4 that has been conducted in the morning session. So basically in the morning section you have studied about different kind of the surfactants and their properties, right? So in this particular case, because we will do the synthesis of further nanomaterials which are being stabilized by the Gemini surfactant in the next lectures and the tutorials, so this particular experiment is being added in this tutorial. Now, first of all, what is the surfactant? I think all of you are very much clear what is the role of surfactant in your daily life, in your pharmaceuticals, in your synthesis and other aspects of your life. But in general terms, we are called surfactant as the surface acting agents, right? So if I am talking about the surfactant, there are different varieties of surfactant which you have already seen in the morning's lecture. First is the ionic, then non-ionic, and third one is zwitterionic, right? So, and other one, last one is amphiphilic, right? So in case the Gemini surfactant is concerned, the Gemini surfactants are more or less related with the ionic surfactants, which are non-ionic in nature, but they are acting as a surfactant, because for a surfactant what you need a polar part and a non-polar part. So in alcohols also, if you have a long chain of the hydrocarbon like cetyl alcohol, stearyl alcohol, right, in those cases you have a long hydrocarbon chain, 12 carbon, 14 carbon chain, right? So that can impart polar and non-polar moiety in the same molecule. So you must have heard about face wash Cetaphil, right? Have you heard about it?
Yes.
So it is not soapy, it is not giving you that much foam, it is milder, but it is used as a cleanser. So it gives moisturizer to the skin, and especially if you have damaged skin and have skin issues, then normally it is recommended. So what is there in that particular face wash? It has cetyl alcohol and stearyl alcohol, mixture of both the alcohols. So these alcohols, they have OH group and they provide moisturizing tendency, so lesser drying effect and cleansing. Of course it is there, it is milder surfactant, right? So zwitterionic, as you know, zwitterion means like most of the amino acids, they are zwitterion in nature, but I think a student asked the question in the last lecture that can amino acid act as a surfactant? But no, because the group is not that large, the non-polar part is not that large. But yes, you can functionalize the amino acid if you increase the length or of the hydrocarbon part bigger, then you can have the zwitterionic kind of the surfactant. So amino acids can be modified into the surfactants. And now I am talking about the Gemini surfactant. So Gemini surfactants, they are which kind of surfactant? They are ionic surfactant, right? So they are ionic surfactant, but here these are not monomeric, right? So can you proceed for next one? So you can see here. So these are again the surfactant molecules where you have the hydrophilic part as well as your hydrophobic part, which is a characteristic property of a surfactant. So you require this thing, polar, non-polar. Right, these two things are definitely required. But now what is the difference between the Gemini surfactant and the other surfactant? You can see here there is a two heads, two polar heads and two tails. Right, so this is a dimeric species, not like a cetyl, CTAB, SDS, which are the monomeric units. So here there is a spacer between the two head groups, the two polar groups, right? And the other one is hydrophobic, or we can also call lipophilic. If something is hydrophobic, it means it is lipophilic, it is fat soluble, and the head is hydrophilic, which is water soluble, or lipophobic. Right? We can use these terms collectively. So the spacer is there. So now the molecule has two polar heads and two non-polar tails. So it will show better effect in the coating of the nanomaterials, in the stability of the nanomaterials. So this can also impart other enhanced surface properties, because these are surface active agents. So the CMC, the critical micellar concentration will also change because of this particular structure. So you can design the molecule according to your application, right? So you can change the length of this part, hydrophobic part, right? You can have 14 carbon, you can have 12 carbon, you have 16 carbon, right? So there are different commercial names based upon the carbon content. I will let you know one by one. So even the spacer is now between these two head groups, right? But there are certain Gemini surfactants in which the spacer can be between two hydrophobic groups, right? So but we are right now concentrating only on the Gemini synthesis of Gemini surfactants which have a spacer on the polar heads, between two polar heads. So our synthesis is related with the Gemini surfactants having spacer between two polar heads, and today's synthesis will be 12 to 12, right? What do you mean by 12 to 12? So 12 carbons in this particular non-polar part, so C12, and the spacer means you can see these two heads representing. So now you have here two carbons, so 2, and again the tail has 12 carbon, so you can represent the molecule 12 to 12. So you can similarly increase the chain length 14 to 12, 14, right? You can 16 to 16, 20 to 20. So you will change the precursor. You can have a variety of Gemini surfactants. So sometimes these Gemini surfactants are very costly, not readily available with the vendors or the suppliers. So you can synthesize your own Gemini surfactant and you can then use in the synthesis of the nanomaterial. So you will not be dependent on anybody for the purchase of the Gemini surfactant. So now whatever I am telling you, this is a symmetrical Gemini surfactant, means 12 to 12. So both the chain lengths of the non-polar part is same, but yes, you can change it, right? You can have 12 to 14, you can have 12 to 16, you have to change the precursor only. That is a simple synthetic procedure that we will share in the laboratory. So next is, this one is the species. You can see that we will synthesize. Now you can change the value of N, right? So as you change the value of N, the properties will be vary because the non-polar part will increase, right? So that part is spacer, and these are again, these are cationic surfactants, because you can see nitrogen has a positive charge over here. This is a quaternary salt, kind of quaternary salt, like cetyl trimethyl ammonium bromide, which is commercial name is CTAB. So it has again positive part, it's a quaternary salt. This is again a quaternary salt, but this, what is the difference? Here you have a dimeric unit where you have a space. Okay, next. Again, what are the importance of the Gemini surfactant? they have a CMC, low CMC. So if you are talking about the surfactant, so what should be the, there are certain properties which I think you have heard in the morning's lecture, their radius, their CMC ratio, right, and the other features are there. So if you want to enhance the property of the surfactant, then CMC should be low. At low concentration, it can create the micellar, right? Then you need a small amount of surfactant to create a micellar. If CMC is high, what does it mean? You require a large amount of surfactant to create the micellar. So if I'm just talking about the cleansing action, the basic action of the surfactant, without micellization, cleaning will not be possible, right? So if you're talking about good detergent, so which is costly, right, then you need small amount. But if you choose the cheaper one, then in that case you need to add the larger amount, right? So it is on the, depending upon the quality of the surfactant they have used, the chemical they have used, right? So the property, first property is the Gemini surfactants, they have a lower critical micellar concentration, lower CMC, right? Surface tension lesser, right? Then thermal and chemical stability you definitely require. So chemically it should be stable so that it should not react with anything, especially the reactant which are using in your synthesis and other experiments. Then tolerable properties, you can change them according to your requirement. Even you can synthesize a Gemini surfactant according to your requirement, right? Next is, so today we will do the synthesis of Gemini surfactant, which I have already told you it is cationic in nature. And what is the 12 to 12? I think, hope everyone is now clear that what is 12 to 12, why we show it 12 to 12, right? 12 carbon, 12 2 spacer and 12 carbon. So what are the common precursors which are used in this synthesis? First one is bromo-dodecane. Dodecane means 12 carbon. Dodecane is the carbon content should be 12. So this one is there. And now we have next is tetramethylene diamine. So this one is tetramethylene diamine. So this part will act as a spacer in your synthesis and it will combine with the bromodecane. So solvent is the ethanol. You will dissolve the contents in the ethanol and after that the reaction will occur. Next. So now in the synthesis, this particular synthesis I am showing the scheme of the reaction which is being undergoing. Everything is okay? We have, you can vary the N. I have shown it in the dotted form. So in the dotted form means the carbon can vary. The carbon N can be 12, it can be 14, it can be 16. So if I am using for 12 to 12, like in today's experiment you are using the 12 to 12, so you will have bromo-dodecane. Dodecane I have already told you, C12. And if you are synthesizing 14 to 14, then bromo-tetradecane. Decane is 10, tetra means 4, 14. So next one is hexadecane. If you are using one bromo-hexadecane, and it will give you the 16. So now you will get the process for the synthesis to 12, 14 and 16 all in same procedure. And then you are using the same other tetramethylene diamine and then tetramethylene diamine. So this one is useful as a spacer element. Now ethanol, and we will reflex it at 80 degrees. Right? So after 72 hours in our case, the product will be obtained. So that will be the product. So now you can see in the first case you will have 12 to 12, 14 to 14 and 16 to 16. Right? So this is the symmetrical Gemini surfactant. Next. Okay, so this is how the process will be carried out. So basically in this particular case, what is the general, if I am talking about the general scheme of the reaction, you have to take 1 mole of ethylene diamine and 2 mole of the bromo-dodecane. So the ratio of the reaction should be 1:2 mole.
1:2.
Then it will give you the final product. So whenever you are using, always you can vary the amount depending upon if you want 1:1, you can choose 1 mole of this ethylene diamine and 2 mole of the second one is the bromododecane, right? So if you want to synthesize in the larger amount, you can take 1:2. If you want in the smaller amount, you can use 0.1 mole and other one 0.2 mole, right? So depending upon your requirement, you can change it. But the reaction is 1:2 ratio. The ratio of the molar ratio should be 1:2. So now you are using the tetraethylene diamine. So both the reactants are liquid in nature, first of all, right? So here we have ethylene diamine, that is liquid, and the second one is bromododecane. They are both liquid in nature. So what we will do, we will get from the moles, we can calculate the molecular weight which is required in that reaction, and then you can check the density of that material from the bottle of the chemical, and then you can use the formula density is equal to mass by volume. You know the mass, you know the density, then how much volume you require you can get from the equation, right? So in this particular case we have already calculated. So in this case you have ethylene diamine 1.8 ml. So this is a little bit excess amount. So second one is the 4.25 ml of the bromodecane. I have already given the density, and we will dissolve this in the 50 ml of the ethanol. So now we will keep it in the oil bath and it will be refluxed from 80 to 90 degree for 72 hours, right? We will start the reaction today, and we have certain samples which we have collected because we have carried out the experiment prior to this tutorial, and we have the samples of each day, and we have the other final pure compound. I will show you all that. So after the completion of the reaction, we will work it up by removing the ethanol, and further we will purify with excess of the acetone, and finally you will get the white color powder product. Next. So this is the samples which we have collected day wise. So you can see in the first day we can add a drop from the sample and then 10 ml of distilled water. On the day 1 you will see the turbidity is there. You know turbidity, you can't see through the sample, then it gives you the turbidity. Day 2 is again the turbidity. Day 3 the turbidity will decrease, and on day 4 the turbidity will completely disappear. This shows that reaction is now complete, and after removing the ethanol and work up with the acetone, you will get the white precipitates. Next. And before that, so it will give you a white powder, like a common salt is there. So same kind of, it's not that crystalline, but it's a powder white compound will be obtained. So now the point is how you will characterize the sample. How will you know? The first is the during the reaction you can have a TLC, thin layer chromatography. I think most of you know. So it is one of the technique to, and simplest technique. It doesn't require any sophisticated equipment or else. So you can simply use thin layer chromatography. You can have a silica coated glass strips, or you can use the aluminium coated strips, aluminium strips which are coated with silica. These are the ready-made strips which you can use easily. So you can monitor the progress of the reaction through the TLC. So once the spots of the reactant disappear, then you will come to know that yes, the reaction is completed. And the point is that whether you have got the desired product or not, that will be characterized through the different spectroscopy techniques, right? If the reaction is complete, that you can find out by TLC. The reactants disappear, right? Okay, then something is formed. But that something is desired product or something else, that only be characterized with the help of the spectroscopy. So now this is the NMR spectroscopy. I think some of the students must be aware what is NMR spectroscopy. So nuclear magnetic resonance spectroscopy, it gives the information about different protons which are present in your organic compound. So in this particular case, you can see this is the NMR of 12 to 12. Right? So if you can see, there are different chemical shift values, and their spin multiplicity, and depending upon the area under the curve, we can find out the number of protons which are present in your NMR, and then you can assign those protons to particular functionality, particular carbon which is there in the group. So in this case you can see you have 12 carbon on that side, 12 carbon below, and 2 carbons in the center as a spacer, right? So first of all you have a signal at 0.88. So this is the triplet. You can see the triplet is there, right? I think the triplet is there before 1. So these are 3 triplets. They belongs to the alkyl, the terminal alkyl group. The first you can see that on that side 0.88. Then you have a next signal. If I'm going through the numbers only, 1.26. So if I'm talking about the 1.26, 1.26 is again a multiplet. So 1.26, all these are 1.26, right? So these all carbons are 1.26. So how many carbons are there in 1.26? You can see the 1.26, we have different carbons. 36 protons are there, 1.2, 6 to 1.7, right? So these are the multiplets, 36 protons are there because 9 CH2 groups are there, right? So next one is 3.68. So these are these belongs to the spacer element. These are the spacer element. Now why they are downfield? Because the nitrogen is there along with that, so they are little bit downfield. Values will be higher as compared to the other one. Similarly, the carbon which is attached to the nitrogen, this will be also downfield. The next one, this one is also little bit downfield, right? The effect is there, right? So in this way you can predict the structure of the NMR. Next. And again this one is particularly belongs to the IR, infrared spectroscopy. So here you can plot it accordingly, wave number and the percentage transmittance. So in this case particularly you can see these are not, there is not a particular functional group in this surfactant. Only we can look into the carbon nitrogen bonds, right? Because there are no amine, primary or secondary amine, right? So in this case you can have the CN around 1100, and other characteristic peaks are there belonging to CH2 group, stretching and symmetric stretching, asymmetric stretching, bending, scissoring and all that. Next. So I think in the morning session you have already discussed a lot about different kind of surfactant and their applications. So definitely they are corrosion inhibitors. Some of the surfactants are used to resist the corrosion. And skin care, I have already told you that there are, like in the shampoos you have sodium lauryl sulfate, right? There are a specific shampoo range which are called sulfate free. They have different non-ionic surfactants. They are at a higher cost, right? So there is a brand, there are different brands, I am not telling you the name, but they describe it sulfate free shampoos, right? Though it affects the hair lesser and they are more milder as compared to the shampoos which are having sodium lauryl sulfate, and the brands are claiming it. I am not sure but they are saying is correct or not. So Cetaphil is there, it's a cleanser which is having cetyl alcohol and stearyl alcohol. And detergents, of course, detergents are there, and there is a separate market of the detergents which are based on the surfactants. And we have soaps which are the fatty acid based surfactants, and we can have the different ionic compounds which are used in the normal detergents. So in the petrochemicals, cosmetics, pharmaceutical, there are certain medicines, certain ointments, especially eye drops which have a lubrication, and they can act like Dr. Bakshi has told that the layer in the alveoli, they are also having the natural surfactant. So there are certain medicines which act as like a natural surfactant, and they can enhance the betterment of a particular patient. Next. So conclusion is, so they have a unique molecular structure because they are different from the conventional surfactant, which are monomeric in nature, right? So they have a single unit of the hydrophobic part, right? They have a different and versatile structure which give it different kind of property. So there are wide range of applications. So even if you synthesize a Jamine surfactant, then you can explore the application of that surfactant in different fields. Whether you belongs to the nanoscience or whether you belong to the metallurgy, you can check the anti-corrosion properties and all. So it's not that only nanoscience can use a surfactant. Even if somebody is doing the biotechnology or in the pharmaceutical or in the metallurgy or in the synthesis and other things, you can use these surfactants as per your own requirement, because their complete evaluation and their application and studies are not yet documented. Right? So, thank you. We will now have a hands-on session in the laboratory, and you will synthesize the 12 to 12 group. Okay? But we have this magnetic stirrer with the hot plate, so it has inbuilt this temperature probe, so you will get digital temperature recording over here, right, in this particular case. So you can use a normal thermometer if you don't have this. You can use a normal hot plate also in this reaction with the oil bath kept on it, and the normal thermometer you can hang it with another stand, right, if you don't have this. So now I have oil bath. This is your condenser. I think you know about this. For refluxing we are using this. One is the inlet, other one is the outlet. So what is the use of this condenser? Yes? Can anybody tell me why you are adding this condenser in this section? So we have this round bottom glass, right? So So in this round bottom flask, you will carry the reaction
Hello.
for 3 days, 72 hours. So now when we fill this with the condenser, so the whatever the vapors which are go from this particular RBF, so they will condense, right, and they will go back to this. Otherwise there will be overheating and all of your reactant will disappear. It will disappear and it will further decomposition of the reaction will. So now I am adding this condenser. So you have fresh water there, right? So in this case you will have inlet for the cold water and the outlet is there for the hot. So sometimes right now we have attached the taps with this particular hose, but if we have a large number of reactions, you can use the fish pump also. So we carry a large container or a plastic tub which is having a cold water. We recirculate the same water to the fish pump, so it saves the water also. We can use it like this. So now we have this RB, we have a condenser which is required. We have applied small amount of grease, which is silicone grease, so that we can easily remove the flask from this. So now in the reaction you have the steam also. You will add you can add. So we have tetramethyl ethylene diamine. So we will add 1.2 ml of this. So this is a micropipette. So you can even use the cylinder if you don't have the micropipette. This is the cylinder which is glass, right? Plastic is also available. So, but this micropipette is more precise. So now we have added the tetraethyl diamine. How much? You have added twice. Okay. The next one is, second is your bromodotative, right? The second reactant is bromodotative and add 50 ml of ethanol. Ethanol is a solvent. It is a solvent and these are the, both have the reactant. This is in the larger amount, so we are using the cylinder. Boiling chip in this, so that pumping will not be there and pumping will not be there. You can add the magnetic field also if you want. Add the magnetic bead for proper stirring, for uniformity. You can also add the ceramic bead also. If you don't have magnetic stirrer, if you are using just the hot plate or not magnetic stirrer, you can use a direct hot plate. So even you can use the water bath, but for 72 hours, for 3 days, non-stop you have to run the water bath and then you have to add water continuously. So that is why we are doing this. Otherwise, for say 80 degree temperature, you can use the water bottle. So we are using this one because this will run uninterrupted for 72. So this one is the magnetic bead. clamp for this RB and condenser. क्लैंप इसके लिए this will fix both the condenser and the RB together. The flask should not touch the bottom, it should be a little bit higher. Stability temperature. Now you can see. Start now. Now it will fill. So you should see the pressure should not be that high. And the continuous flow. The page is rotating, oil after heated, and this is husband. Right? Clear? I hope it is clear. Now you can show me the different samples, the real sample, final product. Water. One dropper plastic. So we have collected the sample from day 1, right? And we have done day 2, then day 3 and day 4. So we have 4 samples from day 1 to day 4. And I have already told you that in the PPT that if you add 10 ml of water and small drop of this aliquot of day 4, you will see that turbidity will not be there. And in case of day 1, there will be turbidity. So turbidity will slowly disappear from day 1 to day 4. So this will show you the completion of the reaction. And when the reaction is complete, after workup with the acetone and all, you will get this final thing. So this is 12 to 12 Gemini that you will get after 3 days when you add, when you remove the ethanol from the mixture, you will add acetone, then you will get the precipitate of 12 to 12, you will filter it out, remove it, and you will get the final product which you can use in the case. So you can add, this is the water and test tube. So I am adding 10 ml of water and in day 1. So this is a sample from day 1 which we have collected from the day 1. Can you see the turbidity? It's a milky, right? So this one is milky. So another dropper added there. Day 4, right? So you will easily compare day 1 and day 4. So I have added 2 drops in both. You can see the difference. Right? This one is turbid and this one show that reaction is complete. So when you complete 24 hours day 1, right? So day 1 you will remove the sample. Like today's, right now we will have first drop. This is 0 day, this is not 4 day. Basically 0, 1, 2, 3. So the fourth one is means fourth sample. I am saying the day, but please correct it. This is not the fourth day, because when you have 24 hours multiplied by 72 hours. So I am telling you it's 72 hour reaction. So it's not day 1, it is day 0. Like I have started the reaction, and then first after 24 hours one day, after next 24 second day, and after next 24 hours that is 72 hours, it will be day third will complete. So this is the fourth sample that belongs to day third after 72 hours. I hope it is clear. Mrs. Anna, I have already shown you how to carry out this one. You will do it your own. I will go to everybody's seat and you will do it in front of me. One by one. The first group. Be very particular about inlet and outlet. Normally students do in opposite manner. Both the reacted? So now what is? So now you will add how much ethanol? 50 ml. Magnetic bead, and then you will lock it with this.
और थोड़ा नीचे
Thermometer. On this side. Okay, so now you will fix it like that. So next one, next group. So the first group will remain there. Whose group is this? So all of you are from second group? So third will stay at their own place.
अब कौन सा ग्रुप
Second first.
फर्स्ट ग्रुप वहीं पे खड़े हो जाओ
किसमें देखो?
पानी का प्रेशर पड़ते ही खुल जाए
उसके बाद में इसमें से एक सैंपल निकालना है थोड़ा, है ना, फिर अगले दिन सेट निकालना।
Read is there? Cosmetic. So you can monitor the temperature with the thermometer, increase that temperature is rising. You can decrease the This is the mistake which most of the students are doing. Outlet and inlet. You need the fresh water. Or you can change the
उसके बाद में डालने के बाद में सरफेस प्रोटेक्ट नीचे टच नहीं होता पकड़े रखो
ये आगे के नीचे जाएगी ना इसको कुछ नहीं करना अब इसको ऑन करें ये थर्मोमीटर का साइन बना हुआ है हीटिंग प्रोवाइड कर रहा है और ये रोटेशन का है रोटेशन कर रहे हैं ठीक है उसकी वजह से ये रोटेट हो रहा है ठीक है ये इसका है ना हाँ ये इससे होगा आ रहा हो गया बस बस अभी देखते कितना हो पाए
what is the actual time for direction conversion. This is a known method, so we know it is available to us. But if it is unknown, then in that way, or you can also do that. one pot or in a different pot. So if you are in one pot, a mixture of compounds, it may be possible that you can use 12 plus 15 to 12 plus mixture of 12 to 15. So now we are using first step will be that 12 to remove the plate, then one of the other part of nitrogen will be nitrogen. So when you sometimes there is a mixture of products formed. So if the mixture of products is formed, then you need to do the following. Right? So in the column chromatography, you have to separate. That is a tedious process. But this is very easy. You will get only one product, and that is easy. So now what we will do, we will check the process of the reaction, like turbidity experiment. So now we will you can also use double neck flask. Water है? तो इसमें पानी डालिए। Yeah. So in this particular case, if you want to, because this is a known reaction, we know after 72 hours the reaction will be completed. So if you want to carry out new reaction, just like I have told you, you can carry the different mixture of compounds. So in that case, you can use the double neck flask. So in the double neck flask, you have the another. Can you show the double neck flask? So in case of the double neck flask, you have the separate neck. From that you can take out the sample for evaluation for the for this turbidity. these are two neck glass. So from one side you can add the condenser, and from the other side you can take the sample very easily without disturbing your reaction. Okay, so you can add like this is a stopper. So if this is the other stopper of different neck sizes there, you can fit it over here. So this is for the this is B24 joint. There are different sizes of the joints in the neck. And this is for smaller. And if when we carry out small amount of reaction, like this is of 10 ml, right? Very small reaction synthesis. So like this. And the condenser is also of different neck size. It will fit over here. The small condenser is there, and we can easily open it like this. Take the sample to the syringe or to the pipe, and you can easily do the TLC. Progress the monitor the progress of the reaction by the silica gel TLC chromatography, and you can see this is prepared already manufactured TLC silica gel. So this is F254. These are UV sensitive, right? Normal are also available. So this one is silica gel 60 F254. So what is the F254? These are UV active, right? So when you, if your compound is UV active, sometimes the spot is not visible under normal visible light. So what you do, you will keep this TLC tape sample in the UV chamber, and you will see the spot, right, for photoactive compounds. So that is why we are using this one. So I will show you. These are pre-cut sheets. I think you have not seen this earlier. This one is alumina coated flexible, and this one is silica coated. So smooth silica coating is there. So in the research normally we use these sheets. So these we cut it according to our requirement, like this one is there. So if you want to mark it, so to the capillary you can add one spot just above this line, right? So then you will keep it in the solvent, right? And in the solvent the spot will rise. Okay, so you should take care of the solvent front and all that, and check the progress of the reaction. So if the spot of the reactant, so what we do the separate spot for both the reactants, so and then the mixture. So 3 spots. So you have the reactant spot to find out that, to compare it with the mixture. So if it is of A reactant or if it is of the B reactant, so you will check the mixture. So if the spot of reactant disappear and a new spot is generated, then it means the reaction is going in the right direction. And second thing is, you can increase the polarity. You will start from polar or non-polar. Which solvent you will use first? Non-polar solvent or polar? Yes? Anybody? You will start from non-polar. Right, like hexane you are using first, and then you will add the ethyl acetate. So different concentration, 10%, 20%, 30%. So when you feel that the spot starts to segregate, Right? Sometimes what happens that in lower non-polar solvents, the product and the reactant, they are very close to each other. The spots are very close to each other. So if you want to separate, you will increase the polarity. So you will start from non-polar and then you will slowly move to the polar. Similarly, in the column chromatography also, you have a silica gel column, and again you will start from the non-polar to the polar. So you will increase the polarity and run that column, and you at different percentage of polarity you will collect the sample, and through solvent evaporation you will collect the final sample. So this is how you separate when you have a mixture of more than 2 or more than 2. So I will tell you how you will make. This is in the chloroform. This is in the chloroform. I think you must be aware about it. Yes. Yes, ma'am. So we have now this one chloroform. So make sure it should be clean. There should be using the solvent like chloroform so that it can easily evaporate, or different other can be used. So you can see it is drying very fast. Clear. You can use this one also in checking the progress of reaction rate. Now this is completely dry. You will see it will turn into pure white cast. Otherwise it will appear a little bit transparent or have a glass-like appearance. Now it is completely ready and it will look like this. So now you will add a spot. What is this spot? नहीं इसी का लगाना है। इसमें solvent we are adding 10% hexane. 10% means hexane ethyl ester mixture. 10% of the ethyl ester, and the like I am preparing 10 ml solution, then 9 ml of the hexane, 1 ml of the ethyl. So that is 10% ethyl ester hexane mixture. 10%. 10 more. day 1 ये 0 है ना, day 1 So now we will do the DLC of the reactants, 2 reactants, and already we have the sample of day 0 and day 1. So we will do the spot. ताकि इनको इजीली, क्योंकि इनको अगर वो will not be possible to have the aluminium chip, so they can So you should take care that the spot should not be too broad. Should be thin. Be छोटी. ज्योति तो नहीं लगी बात. One of the reactant, first reactant. This was the bromododecene. Works like a failure when you release the pressure to drop. What is the Now we will keep this in this chromatography jar. You can use the forceps for this. Let it dry. ये ना, so this one is having another advantage. This is not that the powder is not leaving the slide that easily. This one is having better binder as compared to this. We will cover it for better wafers. different agents for curing. Here we are using the iodine. There are different others. प्रोडक्ट नहीं बन रहा दिखाई दे रहा है उसमें तीनों के स्पॉट्स आ रहे हैं। because we have collected a sample on the date first, so 2 days back. So if we will keep the reactor determining the date, so they will get so that is why they are doing it. If you apply this TLC to your own fresh sample, the spot of the reactant will be much better, and the intensity will be better. So now the intensity is lesser, so still you will see the when you are doing it for fresh samples, then the intensity of the color will be more and the spot of the product will not be. But right now you can see it will get right, so it means reaction is incomplete. But yes, it is proceeding in the forward direction, the color is started forward. Completion of the reaction. Similarly, I have shown you how you will progress the monitor the progress of the reaction, and even you can check the reaction by TLC. So both the methods I have shown you. So similarly after some time interval like 6 hours, you can check the turbidity, and you can also monitor by the TLC after the completion of reaction. Once the reactants are shown disappearing in the TLC spot, as well as it shows no turbidity on adding a drop of compound in the water, it means reaction is complete. After you will evaporate the ethanol, and then the product will be added in the acetone, and finally it will be washed and filtered. So that will give you the purity. So this one is new. So you can also check that figure. So now we have finished this experiment for the synthesis of Gemini surfactant, that is 12 to 12 by synthetic methodology. So similarly, you can synthesize the another Gemini surfactants 14 to 14, 16, 16 or whatever the hand can be, right? So these Gemini surfactants which you have synthesized today, these will be further used for, in the synthesis of silver and gold nanoparticles. So tomorrow you will have an experiment on silver and gold nanoparticles. So these Gemini surfactants will be used in the synthesis of gold and silver nanoparticles, which are stabilized by, which are coated and stabilized by Gemini surfactants, right? And in subsequent tutorials, further these Gemini surfactant will be used in synthesis of iron oxide nanoparticles. So coated and stabilized by the Gemini surfactant. So this is the chain of different experiments. So this is the first step, and the same Gemini surfactant will be utilized in the further reactions. Clear? Yes. If you have any doubt, you can ask.